to current trends in the cyber physical systems. My name is Hans Vangheluwe. Some of you may have heard me earlier, and it is my pleasure to chair this session, which has two major parts. There's first a part with two speakers who are both students at BITS, and who will talk about their research. And then there will be a talk about by Professor Baths, who is also from BITS, and who will talk about the link with computational neuroscience, biomedical engineering, etc. But without further ado, I would like to give the floor to Rakshit Mittal, who, in addition to managing the technical side of this whole workshop, is also a researcher and who will talk about his research now. Rakshit?
Thank you, sir. I hope my screen is visible. And yeah,
Yes.
so I will be talking about the feature-based ontology for cyber-physical systems. And this work had been going on for quite some time at the MPM for CPS cost action IC 1404. I have recently been involved with the same work in developing this framework and uh, this model for cyber physical systems. So basically, we have a feature model here. The modeling paradigm which we are using in this case is a feature model. And what exactly are the semantics of this feature model and this feature diagram, which you can see right here in front of you? Like, what is it exactly? So we, in a sense, in software development and in that industry, we have something called a software product line. We have product lines in general. And if we want to understand the commonality and variability of features between all of these software products, um, something like this feature model can be used very extensively for a high level modeling exercise for in such cases. So essentially, in a feature model comprises a feature diagram in which which is essentially a tree in graphical form, and each element of this feature diagram constitutes uh, it constitutes a feature. A feature is essentially a quality, um, like it is a discernible quality which can be or a feature for that particular product line which is being modeled. And I've taken here as an example a model of a cold chain, like a cold chain system, which we had developed a few weeks back. So what we have exactly over here is that, like, first of all, this is a tree with the root being cold chain IoT. So this is the root feature, and it has certain sub features under it, or like child features called. It has a cyber part, a physical part, a part with humans, and a network. So these features, they'll have sub features. Those sub features will have other sub features under them. And basically, what you do is each feature in this feature model or this feature diagram corresponds to a Boolean variable. So this whole feature diagram, this specifies a product line. And when you want to derive a product from this feature diagram, you essentially have to specify which of these features have to be selected or deselected. So that Boolean variable associated with each feature will either have a value 1 or 0. And to verify whether this product which we have just generated by specifying each of these features being either selected or deselected, whether this product specification is valid or not, we carry out, we have certain rules associated um, in between, like, we have some conditions and specified for uh, for each of these features. So for example, if you can see here, there is a legend, and these features with a dark dot, they are mandatory. So these mandatory features have to be selected. Their Boolean variable value has to be 1. The associated value has to be 1 or true. And correspondingly, we have some empty, like some optional constraints. So these constraints specify that this feature may or may not be selected. And for a group of features like we have here in this feature diagram developed at MPM for CPS, we can have some more groups as well. Like for example here, this is an alternative group. An alternative group specifies that at least one um, of these features, at least alternative. Yeah, so an alternative group specifies that exactly one of these features, one of the child features has to be selected if the parent feature is selected. So for example, if in my product this configuration feature is selected, then I also have to mandatorily select either one of these sub features. So my configuration can either be my network configuration can either be a star configuration or a bus configuration or like whatever these examples are. Similarly, we have an or condition as well. So role, a human role can either be in terms of responsibilities or constraints. So we can either have responsibility specified or constraint specified as well. And at least one of these has to be selected in an or condition. So we have an or condition here, a communication action, a physical action, and an epistemic action in between all of these actions. So at least one kind of action has to exist for any human. And that is how these are the four basic um, constraints that can be specified, which are mandatory, optional, or group, and alternative group. So I hope that you understand like some of the semantics. Like a feature model is very basic. It is like a very high level organization or a high level model of your software product or your software product line, and it specifies the commonality and variability of the features. Uh, Semantics are captured by a propositional formula, and like variables in that propositional formula are nothing but the variables associated with each of these features. And the propositional formulas are nothing more than the constraints which are specified, like mandatory, optional, alternative, or. So these are the four primary constraints, and every program or every product of the software product line is nothing but is like defined by a unique and legal combination of these features. So legality of these features is of course specified or proven by the propositional formula and the constraints associated. And now that I have given you a brief flavor of how exactly a feature model and its semantics work, I will now give you a brief overview of the model which has been developed at um, which has been developed by the group at the cost action MPM for CPS. And so we have this root feature called CPS, and it has certain sub features. So some of its like it has a constituent element which basically models all the actual constituent elements which are under it. And we also specify some non-functional requirements which they have, an application domain. So we can specify the application domain for the CPS or the cyber physical system in question, and the disciplines that it is associated with it, the architectural layers which are a part of it, and so on and so forth. Under constituent elements is where the actual like where most of the work related to CPS happens, because we are essentially modeling the cyber physical system and all of its constituents under the constituent element feature. So this constituent element feature has certain sub features, which are of course the cyber part, the control part, which is we essentially for us, if we are modeling any general cyber physical system, its control part may or may not be associated completely with the cyber part. It may have some control elements which are mechanical, or it may have certain control elements which are which are not explicitly based or coded into the cyber part itself. So to make the abstraction slightly more general, and like more, this makes it semantically better. We model the control feature as separate from cyber part, and we also have humans in the loop. So there is a human part, and we have um, a network part and a physical part, of course. So a cyber part, a physical part, and some other parts as well, like the human network and control part, is what make a cyber physical system. And that is the beauty of a feature model, because it helps us very easily, and you don't really need to worry about a lot of the interconnections, and this is very simple. Like, you can bifurcate the whole cyber physical system into one cyber part, one physical part, and that is why modeling it with feature model is so effective, and it can tell you a lot about the system itself and all of its features and qualities. So a cyber part will, of course, it is nothing but software, and we can have application. So if I go to the cyber part, I hope this is better now, more visible. So cyber part is, of course, software, and we can have types of software: application software, system software, or embedded firmware. Firmware or embedded software doesn't, this typically what we use in many of our devices, which we use in our day-to-day lives, because they do not really have any dependence on some explicit system software, or they do not have any specific application software, but they do have controllers and microcontrollers, which invariably have a software component, and that is how we model the software which is present in such conditions. And system software can be bifurcated into operating systems, system services, system utilities. An operating system can have different kinds of user interfaces, graphical menu driven command line. And so that is essentially how we break down the cyber part of the cyber physical system. And let's look at the physical part now. So a physical part can essentially be modeled as having a sensor, an actuator, or a plant, a controller in itself, and the environment. So we do have a control part, which is independent of the physical part, but that is different from the controller. Because here, what we mean by the controller is the actual physical constraints or the architecture of the controller itself, and not the control algorithm or the control, the control specifications for running that particular cyber physical system. So this is uh, the the control part runs on the controller. It depends, its functioning works on the controller. So it is implemented on the controller. So that is how the controller is different from the control. We can have two types of controls. We can either have an electronic hardware platform, or we can have a mechanical control, like, for example, a thermostat. A thermostat is a mechanical control. On hardware platform, of course, we have motherboards, and like any normal processor in your computer is a hardware platform. FPGAs, all of them come under hardware platform. So under hardware platform, we again have a processor, the memory associated, system buses. We can also specify hardware topology, and we can also have some certain application specific circuits, like maybe a Wi-Fi transmitter, a Bluetooth transmitter, or like um, HDMI interfaces, or some other, like a GPU is already there under processors, but some other application specific circuits as well. So that is how we can model a hardware platform. And let's look at the control now. So the control part of this cyber physical system is actually the most extensive. Um, it is the most extensive uh, subcategory of components of the cyber physical system, and we have, it is defined by its state. It can have some certain disturbances, and input specified for the control and output specified by the control, obviously. And we should specify certain goals for that control algorithm or that control flow to follow. And those goals can be specified as set points, tracking, regulation, reference signals. A control will invariably also have feedback, so that we can maintain, so that uh, so that proper functioning is guaranteed, and that is why we also need feedback. Feedback can be a state feedback, output feedback, and its scope can be centralized, decentralized, distributed. So all of these qualities can be easily modeled using a feature model, whether what kind of feedback is there, what dependencies are there, what scope is there. All of these features can be described using a feature model. And we also have certain dynamics associated with the control. Dynamics are properties which vary over time. So a system type can vary. The behavior of the system can vary with respect to time. The topology of the system can also vary with respect to time. Then we also have certain other properties which can vary according to time, like stability, robustness, adaptation, resilience, heterogeneity, sensitivity, and uncertainty, etc. Then we can also have diagnostics, where diagnostics is the capability of identification of properties in a system, and prognostics is prediction of the time in the future when a system will not perform as expected. So these capabilities are also very important for a cyber physical system, and they can be modeled in this way. Then we also have a human part and a network part, which are pretty understandable because we do require humans in the loop as administrators or activity performers in your cyber physical system. And we have application domains. Yeah, so that is pretty much the model which is being developed by the group at the cost action IC 1404 MPM for CPS. And what uh, this how does this feature model help us in MPM? Like, okay, so we have specified these features. How is it useful? How does it help us move on to the later stages once we have developed these features? So once we have our product and once we have specified the features which that product should have, the next step is probably if um, identifying the dependencies between these qualities and identifying the software, like the software or the implementation in the further steps, which of those what parts of those implementations correspond to which parts of the feature model, and if that part in the feature model is selected, then concurrently that part in the further steps, like software in the loop or hardware in the loop, so that object should also be present, that object should also be implemented. And that is how some certain aspects of the software product line development can be automated using feature models. And that is where feature models are really useful. And that has been my work with this group. So yeah, I think that concludes my session. I hope. Are there any questions?
Thank you, Rachit. In the meantime, I've asked for questions on the Slack channel. I haven't seen any yet, but maybe in the meantime, I have a question. So indeed, you nicely made this link with feature models and product line engineering. You may have to refine this current feature model with more and more constraints, interdependencies, certain features, configurations that are not allowed at the same time, because if you then go downstream, that wouldn't lead to a meaningful tool. Is that your main goal with this? Because obviously there is value in this by just providing insight. Classification leads to insight. But is your ultimate goal to somehow have a push button approach to saying, I want this feature, this feature, this feature, you push the button and out comes a modeling, an MPM tool, let's say?
Well, I would say that can certainly be. I think that would be like an ultimate implementation of feature model, because right now I'm guessing whatever implementations of feature models are there, they are not really that robust. So most of the times feature models are used in developing the documentation for these products, because documentations can be generated very easily because documentations have certain parts, right? So if a part is not there in a product, then that part need not be there in the documentation. And then we can also look at dependencies and everything. But I would say your suggestion, right? Your like what you said, I think that would be like an ultimate implementation of feature models, and which would give it the most. I would say which would give it the most amount of what is the word for it? value. It would give it
Yeah.
the most amount of value of feature model.
Okay.
And yeah.
Okay, yes. Yeah, I think this is very interesting. And there are examples where this is indeed used in such a generative approach. And there are tools like Claver, class and feature modeling, which allow you to, with bounded exploration, explore the space of all the possible configurations, which can actually help you in figuring out, well, that maybe you haven't added enough constraints yet. But maybe
Exactly.
we can discuss this further offline. I don't see any other questions in the Slack channel, although I see that Rima is typing, so maybe a question will be coming. But given the time, we should move on, and we'll go to the next speaker. The next speaker is Rochishnu Banerjee, who will talk about formal verification techniques. And thank you, Rakshit, for your nice presentation.
Thank you, Hans.
Yes. May I begin presenting?
Yes, please go ahead. I think Rakshit will let you share your screen.
Okay. Rakshit, there's been, I'm not allowed, I think the host hasn't allowed yet to share.
Let me see. Forgotten what I did last time. Do you have the option now?
Yeah. Okay, so is my screen visible now?
Yeah.
Okay, so good evening, everyone. I'm Rochishnu Banerjee. I'm a third-year student at BITS, so I'm 1 year junior to Rakshit, and I'll be presenting a brief talk on formal verification techniques, briefer than I had actually expected because we have less time. So to begin, obviously, we need to know what is formal verification. So we define formal verification as a mathematical way to define a particular behavior of a system, in our case, a cyber-physical system. It develops its own formal model and it describes the properties of the model formally too. Now, formal verification is relatively new if you compare it to formal validation, which existed before. The difference is that in a validation, we only have a formal model and we examine its behavior through simulation or prototype evaluation. Whereas in verification, we need a rigorous mathematical proof. Now, we can obviously think about why did this happen? So why do we need verification? So I could explain this using this example here. So this was a terrible accident that happened in Arizona, a self-driven Uber accident where a cyclist was harmed. What happened is that naturally there was an investigation conducted. Why did this happen? And they found out that the sensors that is supposed to detect whether there is a passerby did detect the cyclist. So it wasn't a case of the sensor failing or the hardware failing, but a case of false positive. So even though there was a bystander, the command given to the car was to keep going and not stop. So because this sort of mistake is an inside mistake, so there must have been an error in the underlying code that was implemented. We need a mathematical proof because a mathematical proof will get rid of all these errors that might happen. So this is why we need verification. Now to the main topic. So what are the techniques that we can use to formally verify our system? So we have automated theorem proving, which is the most widespread use for formal verification. And then we have model checking. Model checking is a very old concept that was developed. So it began with a symbolic model checking, and then as there were new constraints and new problems that emerged, we can classify them into three groups: as symbolic, bounded, or satisfiability modular theory. Next, we have equivalence checking. This is something that I worked on myself with Rakshit and Soumyadip sir. And lastly, we have static analysis, which is a new program that is coming up. These are the techniques. They have their own pros and cons, and we will be looking into them right now. So first of all, what is automated theorem proving? So automated theorem proving is basically a process where we get statements from our system, and with having certain axioms regarding those statements, we develop a certain theory using tools that we have, and we try to prove those certain theories using an ATP engine. This is basically the diagram. So we have our system, and from the system, we have few statements. And from whatever statements we get, we have our own developed theorems. We use those theorems and a proof construction to find whether the statements are true or false. So it relies heavily on higher order logic and uses mathematical structures to build formulas that correspond to the behavior of the system. The verification process is basically the evaluation of these theorems. Now, projects of any complexity can be applied in this method, which is why this is most widely used. So any complexity, so let's say an aircraft or a satellite to a very simple, like an automatic lamp, we can use an automated theorem proving. However, the problem is this requires a very rich knowledge of the formal language that we are using. So the logical reasoning is very important. So this also involves very complex formulas, and so these are few negatives to this one, that you need to have a proper corresponding understanding of how this works. This is basically our automated theorem proving. Now we move on to symbolic model checking. Symbolic model checking works with a set of symbols. It basically uses Boolean decision diagrams to represent a set of states and to work with them in bulk operations. This is basically the definition. Now, what are BDDs, or Boolean decision diagrams? So Boolean BDDs are basically Boolean functions in canonical form, where we can trace a path from a root to a leaf, and a final leaf will basically tell you whether the certain operation is satisfied or not. So this symbolic model checking is done in 2 steps. So we have step 1, where the temporal logic is defined for our system along with the model itself. And once we have the model developed, we have a tree, temporal logic tree, and based on the temporal logic tree, we check for every Boolean function whether we traverse through the tree to each leaf node, and we check whether it's true, in which case the property will hold, or whether if it is false, meaning that the property does not hold. So this is basically our symbolic model checking. The problem with symbolic model checking is that as the systems get more complex, as the CPS get more complex, there is a state explosion problem. So the number of states increases, the number of variables increase. And so traversing and then finding out whether each property holds and in what case becomes very tedious. So this sort of error can be removed by something that was called a bounded model checking, which came into the picture later. This basically uses the propositional decision procedures, SAT, to model the system, which is basically similar to our BDDs. And what we do here is that we have a fixed length, say K, until which we can traverse and check whether we reach a true statement or a false. So this limits the number of counterexamples that can exist. So despite this this kind of model checking we don't generally use for cases where there can be injury, like the self-driven car example that I showed in the beginning, or for important cyber physical systems like aircrafts or something. But this is used mostly as a quick way to check whether any small low-level cyber physical system is correct or not. Next, we move up to SMT model checking. This is a very new theory that has come up. SMT stands for satisfiability modular theories, and it's a problem of deciding the satisfiability of a first-order formula. with respect to some decidable first-order theory. So in this, it is basically a new concept. So here, the first-order formulas are also SAT procedures, just like our BMC, which is the bounded model checking, and they deal very well with the satisfiability part. So we have a first-order theory, and on the other hand, we work with predicates and help to create a decidable logic that is more expressive. So one important contribution of this technique is the creation of a library to standardize SMT tools that can help to spread among different areas and apply these tools for different purposes. So this is a very versatile tool that can be used. And next, we have equivalence checking. So this is something I've worked on before. So with Somadip sir and Rakshit. So here what we did in our project is we took a C program and we converted the C program into a Petri net. So we had a source C program, and similarly we had a translated C program. And the translated C program we also converted into a Petri net, and we tried to check their equivalence. So we used the biosimulation method in this, and this is a part of some research that I have worked on. Broadly speaking, equivalence checking is basically we have two implementations of the same system with different abstraction levels, and we prove that they're functionally equivalent. So they work in the same way. So this technique, this technique is also very versatile, and we can work with many different languages and processes. So like I said, we work with Petri nets, we can work with BDDs or register level diagrams and so on. So a very useful property of equivalence checking is its portability. So if we have a very complex diagram or a system, we can try to convert that system or translate the model of the system into a language where we can easily check for equivalence. So we can just check the equivalence for that system where we have a low-level language, which is much easier to prove, and then we can translate it back into our original complex language. And equivalence checking says that since these translations are equivalent, so the programs must be same. So this is something about equivalence checking. And finally, this is a very new statistical analysis. This is a new technique that they have developed. This is the umbrella methodology, so it has several techniques it can work on. So it was pioneered by Kusa for abstract interpretation of software structures. From that work, numerous tools emerged. For example, the linting that we use in normal computer programs and codes, this was developed based on our static analysis. So unlike simulation, the symbolic execution exercises a program or an architecture using symbols of the values of variables and memory elements instead of a constant value of integers or strings. This enables the variable to accept any value according to its type. Consequently, the command statements assume symbolic expressions as a result instead of an evaluated constant. Furthermore, it is possible to have symbolic expressions for branching conditions. So this is basically static analysis. Here we have a table. So this is basically the different techniques that have been used. So we have the automated theorem prover. These are few tools that are used. So PVS, PMethod, and Isabelle are tools that are developed to check for ATP. Then we have symbolic model checking with NewSMB and UPAL. I have begun working on UPAL along with Dominic sir. So I'm a little bit new to UPAL, but this is currently my main area of research. So these are basically few examples. So bounded MC, we have CBMC and LLBMC. For satisfiability modular theory, we have ESWC, CBMC, and NewXMP. STP is basically simple theorem prover. That is like the basic first theorem prover that was developed. Equivalence checking, we have few examples like Samatulyata and Equip and LRIF. Samatulata is the equivalence tool developed by Samadip sir. And for static analysis, we have CLI or Microsoft Sage or CompCut. And these are basically the industrial uses of these tools and techniques. So ATP is mainly used for processor manufacturers. So we have AMD and Intel working on that. And the symbolic MC model checking is mainly used for much larger complex mechanisms such as weaponry or aircraft. Bounded MC is used mainly for circuit-based systems, just as I said. It's generally used for low-level work because it doesn't have very good safety features. And we have SMT model checking, which is working basically generally in telecommunications area. Equivalence checking has variety, so it is pretty much used in the entire field of cyber physical systems. And we have the static analysis, which works mainly on program-based systems. So it involves like C code or Java or Python, and works mainly in these areas and not in some hardware language level. So this is basically my presentation. Obviously, I would like to acknowledge Saumadip sir and Dominic Proin sir, first of all, because they have guided me throughout my student life for last 1 year or so, and they have gotten me into this interesting field of cyber physical systems, which I'm really liking because I'm still a third year, right? And obviously Rakshit Mittal, he has basically been like an elder brother to me. So he's my senior and just guiding me wherever I'm going. So just making sure that I don't stray away from it. And I would like to thank them, not only for guiding me and to organize this beautiful seminar. Thank you.
Thank you, Rochishnu, for a very nice overview and for your enthusiasm about research. I'm looking at the Slack channel again to see if there are any questions. There aren't any yet, but I have a question. Well, I see someone is typing, but while they are typing, I will ask my question. Yeah, you mentioned that you went from C code to Petri nets. You abstracted from C code to Petri nets, and there you did analysis.
Yes,
and so actually 2 questions. The short one is, what tool did you use to do your analysis, your PetriNet analysis, or did you write your own?
So we developed our own PetriNet analysis, and then we used the biosimulation to basically divide it into parts, and then showed that in the 2 models that we have, there will be a corresponding path from one to the other with the same pre-places and post-places and the transition condition. So hence, each corresponding place or transition has one corresponding element in the other one. So hence, they must be equivalent.
Okay, I see. Okay, good. And then maybe the more general question is, what is your opinion about the sort of workflow? You can start from an existing C program, and which was obviously designed to satisfy certain requirements. And then you can abstract it to the PetriNet level and do analysis there. You could, of course, turn it around. You could start from your requirements and start with a high-level design as a PetriNet, and maybe every place corresponds to basically a basic section in your code, but you don't develop the code yet. You just look at, maybe it's distributed, it's concurrent, there's synchronization. You focus only on those aspects, and the actual details of the code are going to be a refinement of your PetriNet. So what is your opinion on this? And rather than taking existing code, well, why not start from requirements, build PetriNets, verify them, look at alternatives, verify again, and then do refinement?
Yes, sir. That would be a very nice way of working, because that reduces that sort of eliminates all the constraints that we had on the code to begin with. However, the thing is that during the process of making these PetriNets from the program, we generally face a lot of, let's say, hurdles. So there are some parts of a program that we may not be able to sort of verify using the PetriNet, like loop shifting or things like that. So that is why we sort of take the code first to make sure that we can definitely create a model out of it and then work along with the model. So, but it would be really good to try from the reverse direction, start with the PetriNet.
Yeah, and then maybe restrict yourself in what kind of code you use. Well, maybe there are, for example, a while loop. Maybe in real time safety critical code, you're not allowed to use a while loop because it could loop forever. You can only use a for loop and so forth. In safe C or Misra C, this is a constraint. But there is a question by Sejal Gupta. Can CLI be considered as an equivalence checking tool as well?
I have not read through Key before, but I think we did when during one of the research times with Samadit sir, I did spend a little bit of time using CLI, but so CLI can be used as an equivalence checker because it provides the code, it generalizes the code into its variables and how the variables work. So I haven't worked with it, but I would definitely love to look into that. So.
Okay, thank you, Rochishnu, for your talk. And we will move on to the next speaker, who is Professor Veeky Baths, who received his PhD degree in science from BITS Pilani. He is currently an associate professor at BITS Goa Campus, where he heads the Cognitive Neuroscience Lab. And he has received many prestigious national and international grants. And he has a very diverse research interest collection, including computational neuroscience, biomedical engineering, brain-computer interface, systems biology, biomedical and neural signal processing, machine learning, bioinformatics, and so forth, which are all really exciting areas where obviously modeling can be very useful. And his talk is BioCPS, EEG-based Brain Computer Interface, Automation and Control of Internet of Things devices, using augmented reality interfaces for able as well as differently abled members of society. Professor Baths, I look really forward to your talk. This is a very exciting topic.
Okay, so thank you so much, Professor Hans, for the nice introduction. Let me share my screen. I think it's visible to all of you. I think it's been shared here, right?
Yes.
Yeah. Yeah, so thank you so much once again, Professor Hans, for the nice introduction. And so I'm heading the Cognitive Neuroscience Lab here at BITS Pilani Goa Campus. And currently, we are working on three important areas. First one is, of course, brain-computer interface. It's related to home automation and regulation based on EEG signals produced in the brain. And the second one is on Alzheimer's dementia detection using machine learning and deep learning. And third one is about consumer perception and consumer neuroscience. So today, my talk will, I'm focusing mainly on the brain-computer interface and how brain-computer interface, if we'll integrate with IoT technology, how it is going to, address serious neurological disorders. So today's my talk title is EEG-based brain-computer interface, automation and control of IoT devices using visual identification and augmented reality. So this is the outline of today's presentation. So brain-computer interface, it acquires brain signals and then translate them into commands that are relate devices that carry out desired actions. So this is the only technology by which a person suffering from serious neurological disorders can communicate to his or her environment or interact with his environment if he or she is suffering from, let's say, amyotrophic lateral sclerosis or serious spinal cord injury. So what this technology does, it completely bypasses the brain's normal output pathway of peripheral nerves and muscles. So you simply connect, let's say we are using the wireless EEG and we connect it to the computer, and based on the thoughts, there are some actions. So it's very useful for people suffering from serious neurological disorders. And Internet of Things, right? We can always use this technology to integrate. It's a network of physical devices embedded with smart softwares, electronics, sensors, actuators, which enable this object to interact and exchange data in real time. So the advantage of using this is what we can do. So can we have, like, I cannot get the full screen. Can you help me, Rakshit? Yeah, Rakshit, can you hear me?
So if you press F5, I think that should do it.
It's not, okay, 1 minute.
Yes, sir.
Okay. Yeah, so I cannot see the full slides.
But we can.
We can, sir. We can see
we
it.
see your entire
We can
slide.
see it, right?
Yes, sir.
Yeah.
Okay, thank you. So the IoT is the network of physical devices with electronic, software, sensors, network connectivity, and which enables this object to collect data and exchange data in real time. So this technology is, I think, when I talk about brain computer interface, it's like connecting your brain with the computer and translating the thoughts into some actions, right? So this technology, when we talk about integrating BCI technology with IoT technology, what it does, it can help create innovative and beneficial learning monitoring systems or activities for patients suffering from mental health disorders like autism, spectrum disorders, or ADHD. Okay, and also the EEG signals, it is now possible to detect if a person is exhibiting some, or showing some neurological illness. This can be used in advanced health monitoring or tele-healthcare industry. EEG analysis can also be used to detect basic activity like eye blink, attention, and it can be used in automating and controlling the home appliances in the home environment. So before I go more in detail, like what is the current problem we are facing? So there are two important issues which we are currently facing about disability and neurodegeneration, and the other one is depression and mental health disorders. So as per the WHO data, 2 to 4% of the world population, they live with disabilities that severely affect functioning, and 5 to 15% of the disabled population have access to assistive technologies. So conventional methods which people they use for appliance control, they focus on remote controls, providing an interface, use of buttons or keys and touch screen for control. So assistive systems are ineffective for people suffering from, I told that, amyotrophic lateral sclerosis, locked-in syndrome, full body paralysis. So think about these people. They cannot use this touch screen or use of buttons because of these serious neurological disorders. Coming to the next statement is about mental health disorders. So 1 in 4 people will be affected by mental health disorder in their lifetime. It's the data from WHO. And Lancet says that 1.1 billion people have mental health disorders. And 150 million Indians, they need mental health care, and less than only 30 million, they are seeking the care. And reason is, if you see the supply and demand side, there is not adequate training and lack of awareness. Like people, they don't open up about their mental health status. It's a social stigma. And also the number of psychiatrists and number of our population, you see the ratio is very, very bad. So we need some novel intervention strategies or some technological intervention where these serious issues can be addressed. So the motivation came from the fact that the lack of support services like access, information, and communication can make disabled people overly dependent on their families, which prevents them from being economically active and socially included. Okay, so to achieve centralized control and automation of devices is an important step for improving ease of living at home and elsewhere, and to address the daily important challenge for elderly people and for people who have lost motor ability partially or completely, to perform simple everyday actions such as turning on and off lights, opening a door, or accessing controlling TV menus independently can potentially boost the quality of life of such people, and to infer mental health disorders and cognitive behavior using eye movements, and to provide remote health monitoring to medical experts for continuous observations and feedback. So these are the stuff which, we can do it. The number of, I showed you the statistics from WHO, people suffering from neurological disorder or disability, how they can be given some alternative assistive technology which they can use and they can perform their daily routine activities. So these are the technology where brain computer interface and IoT technology can help to find some novel intervention strategies and address these serious, neurological disorders and disabilities. So if you see the national and international status where people have created an augmented reality based BCI and ICPS system for disabled people, then Thomas et al. Have studied the effect of virtual reality on cognition. And there are few works, they have done, used a very hybrid system. So what we are trying to do is we are integrating eye tracking technology, the EEG technology, and the augmented reality technology in unison to address these serious neurological disorders and mental health disorders. Okay, and little has been done to create a system that can facilitate remote access of brain data by an authorized doctor. So it's like accessing brain data in real time. And I told you the poor state of affairs if you compare the ratio of number of psychiatrists and the number of people suffering from these neurological disorders and disabilities. So this is our previous work. What we have done using this is a work which is we have implemented a hybrid BCI system for home automation. And the system works on combination of two responses. One is steady state visual evoked potential and eye blink artifacts. And the USP, I can say the beauty of this system is that it is GUI free implemented. Okay, it's a GUI free implementation and help those with logged in syndrome. And it's a lightweight technique with high accuracy. And we have published in System Man's and Cybernetics this work, and we have filed a patent also. A system and method for controlling a plurality of household appliances. So this is the work. You can see the developed system was implemented with a table fan and lamp with 4 subjects, and we have used 2 steps. One is eye blink, and the other one is SSBP technology. So steady state visual evoked potential is when, let's say, one LED. It's flickering at 5 Hz, and if you are looking at it, and we have put a wireless EEG headset. So in your EEG, it will also show 5 Hz or it's harmonic. Okay, so 5 Hz, 10 Hz, or 15 Hz. So that can be used. Okay, so let's say I can attach that LED which is flickering at 5 Hz to a table lamp. So when the subject who is wearing a EEG headset and he's looking at the LEDs which is flickering at 5 Hz, that means he has selected that table lamp. So device selection has been done. So this SSBP technology is research hotspots, and reason I'll tell you, the SSBP based brain computer interface, it's a research hotspot because the information transfer rate is very high and signal to noise ratio is high, and it is very handy and portable. So that we did, and you can see the SSBP accuracy and eye blink accuracy, the response time, and the transfer rate, that is command per minute, for our previous work. So the current work which we are doing is trying to build a robust BCI methodologies to control remote devices and for differently abled and members of the society to live independent life, and to create a hybrid system of easy eye tracking and augmented reality for establishing a connection and using this to infer the mental health conditions of the subject, and to have a mechanism to confirm the user's intent through steady state visually evoked potential while focusing on augmented reality stimuli, and to create a mechanism for identifying the remote devices that uses the real-time data with the help of image processing and machine learning. So I don't know whether you can see the full slide. So the right-hand side of my screen, you can see the similarities between Internet of Things and central nervous system. Okay, so you can see you have the perception layer, right? Then you have the network layer, and then you have the application layer, right? So sensor actuators. You can see in Internet of Things, it can be your EEG headset, it can be your eye tracking, they collect your eye data, and then you can have the augmented reality headset. And in network of nerves, you can see in the central nervous system, the networking components and sensors you can see. Then the spinal cord, it's a distributed networks of data processing nodes and smart gateways. Then you have the brain, which is the processing and data management unit or data center. So you can easily see the similarities between the architecture of Internet of Things and central nervous system, right? So your brain directly or indirectly can sense lots of stuff. So you can sense, you can perceive, it can hear, you can make decision and comprehension, and then it can process the information. Okay, so that is the reason why I talk about how we can use these sensors like EEG or eye tracking and augmented reality headset and try to understand and connect this device so that it will help in addressing those serious neurological disorders or people having mental disorders. Okay, so and you know that the number of devices on internet has already exceeded the number of people on internet. Okay, and think about the repercussions when you have so many stuffs like EEG, eye tracking, augmented reality data or on the internet. Okay, so augmented reality is a technology which introduces virtual object in the real world in real time, thus enhancing the user's perception of reality. And this is something which people, they use this technology for neuro rehabilitation and augmented reality based brain computer interface as well. So what it will do, so we have EEG set which collects the brain neural correlates or brain data. Eye tracking, it collects your eye movements, like it captures data like the saccade, the fixation, the smooth pursuit. Okay, and there is a strong correlation between your eye movements and your cognition. Okay, so this kind of technology, when it will be integrated and you have this hybrid model, a hybrid system, I think you'll get better understanding how the brain works, right? So this is the system architecture and process flow. So you have three systems integrated. All these are all heterogeneous, so you can have a unique identification number for that. You have the AR data from augmented reality headset. Then you have the eye tracking data you can get from the eye tracker and the EEG data, right? So the eye movement analysis and scene analysis can be done, and you have the video-based corneal reflection, then people-centered corneal reflection. For EEG, you can do the EEG analysis, pre-processing, feature extractions, and feature classification. And for augmented reality headset, you can have a device frequency association with virtual objects to aid in motor imagery-based BCI. And finally, you can see, you can do the SSBP analysis, the frequency features, eye blink artifacts. Then from eye tracking data, you can get fixation information, the saccade information, then smooth pursuit data information. And from, again, eye tracking, when you do that and approaches like, the selective search algorithm will help in object identification and the device classification. Okay, and finally, this can be done, to do or automate appliances, then to infer the mental health conditions remotely, and it opens door for the pervasive healthcare. So this system, it will provide you the multimodal cyber physical system comprising of an EEG headset, eye tracker, and AR headset, which can control and automate a remote device with high precision. And it can provide the augmentative and alternative communication devices, will be very helpful for people with progressive neurodegeneration and disabilities. It will also provide you a system to correlate the brain signals, that is the EEG, and the eye movement information, and it will give you key insights in the field of mental health assessment. And it's a system that can be connected to external web services that further it can help doctor to view and assess patients' mental health remotely. And the societal impact, you can see the combined power of BCI and IoT will offer disabled people with the kind of support system they need to achieve a good quality of life, and they can be integrated to your mainstream economy if you have this kind of alternative augmentative technology, which can help the people or the country to integrate those people into the mainstream economy. And combined use of wearable devices like EEG and eye tracking, it will help you collecting contextual data in everyday life. And the eye tracker and EEG system will help us in understanding and assessing health disorders like autism, dyslexia, and Alzheimer's disease. Okay, and it will also create a system that evaluates learning tools designed for dyslexic kids. Okay, it will plug the gap of mental health professionals in India by facilitating remote services. Okay, so I think that's it from my side. Thank you for your time and attention. If you have any questions, I'll be very happy to answer your question. Thank you so much.
Thank you, Professor Baths, for a very interesting talk and a very exciting area with, of course, incredible impact. As you said, societal impact can be enormous. As is not surprising, there are lots of questions already in the Slack channel. The first one, some of them I think have been partially already answered in some of your slides. The first one is, how does the brain-computer interface measure the brain's output? Does it measure brainwaves frequency or intensity or location or something else altogether?
Yeah. So when we talk about the visual, perception or anything related to visual processing, so your occipital lobe of the brain is, the neurons associated with the occipital lobe, they fire or those neurons are in actions. So we have electrode which is specifically a standard electrode for occipital lobe. It captures data. So the EEG, the electroencephalography, what it does, it collects the data, the electrical information of the brain, okay, and it gives you different frequency in terms of delta, theta, alpha, beta, and gammas. And it depends on high frequency waves or low frequency waves, and based on that, you can understand the cognitive state of an individual.
Okay, thank you. I think the next question by Rakshit was, you've probably also now already answered it. What is the platform that you have used for measuring EEG? Was it locally developed? Is this standard or is it something that is locally developed?
Yeah, so it's not locally. So we use a proprietary software, okay, and that is called NetStation software, and it is integrated with MATLAB. And then we customize. Let's say if I want to work on visual processing or visual perception, I can silent other electrodes and I can take data from that particular area only. So that we use NetStation software from EGI. It's a high density, dense array, EEG system.
Okay, I see. And do you use neural networks to integrate all these inputs and to classify,
yes.
to train and to classify?
Yes, yes.
Okay, yes, yeah. And this is also something that for which you use MathWorks software, or is this something you develop in-house?
No, so we use the commercial software to get those data. Yeah.
Yeah. The questions keep coming in at a rapid rate. Does the eye blink detection tool require a subject to have a normal eye vision? Because obviously you said, well, these are people who may have some lesser abilities.
Yes, so this is a nice question.
What if they can't see? Then
right.
that's an issue, of course.
So the eye blink detection tool requires a subject have a normal eye vision. So those blind or having some abnormalities, it will not work. Yes.
Yeah, and maybe related to this is the continuation of the question. How does BCI differentiate between deliberate and accidental actions? Because very often.
So the deliberate and accidental actions, like what we are doing, we're working on human subject, okay, and we train the subject and we take the baseline data first, okay, and then if it is deliberate, we get different frequencies. We can you can make out from those frequencies.
Okay, yeah. So you can do that kind of classification based on some spectral analysis or so.
Right.
Yes,
right.
I see. And another question is, assuming the eye tracker is worn by an individual and hence not very large, how exactly is the processing of machine learning algorithms and the rendering of complex AR done? Will there be a chip attached with the device, or will it be connected to a network? This is often a problem, no? Maybe you need very high computational power. Is this all done in a lab setting, or do you actually envision someone walking around with some hardware attached? How does this work?
So we are trying, and we are doing it in a lab setting. Okay, so we are not taken it to the commercial level, but we are doing it in the lab setting. And yeah, of course, it changes when you have the complex AR. So we are using very simple augmented reality headset, and there are, like, we change. So eye tracking, what it does, it gives you first data about the saccade, the fixation, where the subject is fixating, and saccade, your random eye movements, and then smooth pursuit. Okay, so we collect those data first, and we see the response, and then again we coordinate this, connect this data with augmented reality headset data.
Mm-hmm. Yeah. And that is then because I've walked around with some of these AR things on my head, and well, very often there is either a cable attached, or there is some very high bandwidth wireless connection. How does this work in your case?
So we have just started this work. So I'll tell you that, in our case, the system which we use, so the data transmission and the communication, it's again, we use the RFID, then BLE, then you have 6LO, WPA, and all those systems which consumes less energy, less power, and all those stuff. So yeah, we are fixing it because these are all battery powered. Okay, these are all battery powered devices we use. Yeah, we are working on that because we face difficulties for, because these are all heterogeneous devices. Okay, like your augmented reality, then you have eye tracker, then you have the easy system. So these are all, so you all this heterogeneous device, they need one unique identification, and then they're all battery powered. So power consumption also is an issue. Okay.
Yes.
Yeah, we are working on that, and yes, once we get some good results, we'll share more about that. Okay, so how this the whole hybrid model works, and what it can do to the current people who are suffering from serious neurological disorders.
Yeah, and as you mentioned, it's hybrid. You have different sources of information. Do you actually cross correlate them in the sense that one way of sometimes filtering out erroneous or noisy data is by somehow comparing it with another data source? So because you have multiple sources of information, maybe you can use that to filter.
Yes, so very nice question. Yes, so all biosignals, they are very noisy. Okay, so all biosignals, they are noisy, and of course we have existing literature, and there are data on the public platform where you can compare and contrast and see the differences. So if you have I told in the beginning about the relation. There is a strong relation between your eye movements and cognition. Okay, so people looking at your eye movements, they can, or psychiatrists looking at your eye movement, they can tell you about your mental health condition or mental health status. So what beauty of this work is, you are collecting eye data also, and the neural correlates of those eyes, right? So there's a strong correlation. So that gives us better understanding. It's not, again, brain, how it works, still it's an enigma. We don't have answer to Alzheimer. We don't have answer to Parkinson. We are simply managing this. You don't have remedy for Alzheimer or any serious neurological disorders. So using this kind of hybrid model, I think it will open up new avenues for where people can find some intervention strategies using this kind of hybrid model.
Yeah. Thank you very much. I see there are no more questions, and then what remains is to thank you for your very nice presentation, to wish you success and lots of impact with your future research. I also thank the many people in the audience, the virtual audience, who have asked questions. And this concludes this session. Thank you, everyone.
Thank you so much, Professor Hans, and thank you everybody for your time and attention. Thank you so much. Thank you.
So after that, there is a, I think, 12 minutes. No, it's a 22 minutes break. So we will come 7:30. It's a virtual coffee break. The session 3 will start after that. In the session 3, there is a one talk in the AC for CPS track and 2 talks from the EDU for CPS track.